Thanks to Roberto and Paolo for getting us together. It's certainly a challenge. First time at this kind of a meeting, and you also assigned a title. That's also happened for the first time. I changed it slightly. I changed it from non-equilibrium thermodynamics to stochastic thermodynamics. I think this is somewhat more narrow, but it's also already more mature and more comprehensive. And the idea of this presentation is that I tell you about the basic principles, about the theorems, but I also want to illustrate it. And I want to show you roughly the logical structure, how students could be led from what they know to these new topics which emerged over the last 20 years or 15 years or so. That's the idea. And I like to show this kind of slide at the beginning of such a course because it relates to what they might know, classical thermodynamics. 200 years ago, people wanted to understand how the different forms of energy get converted into each other. And then on the right-hand side, you see this smallest rotary machine, a single enzyme. We have one ATPase, which usually synthesizes ATP, which is the basic fuel in our cells, but which can also work as a motor. And you can, if you attach a big sphere to it, you can apply an external force or torque, and then you can let this little machine run against this force and do work. And one basic difference, of course, between this machine and this machine can be shown in this diagram, where you see the angle of this little subunit as a function of time, and you see clear steps, 120-degree steps, and of course one sees fluctuations. So the question is, and it's a non-trivial question, whether the concepts which have been developed to understand these microscopic machines can be applied to these much, much smaller little machines. And to emphasize this, it's also good to show the range of scale which are involved. So this is power, this is length. Steam and car engines are up here, and single molecules are down there. And we talk about 24 orders of magnitude in power in this equation. And of course, as you know, it's about 6 to 9 orders of length scales. And it's not obvious whether what has been applied up here or developed up here can be used down there, and how it can be used. Okay, so much as just one possible motivation. Of course, there will be many others, and I think Sergio will talk about other experiments tomorrow morning. When we talk about teaching, we always have to understand or to be clear on what should students know. I think they should know a little bit of equilibrium sub-mech. It doesn't hurt to know a little bit of thermodynamics. But I put it in brackets because when I teach that, and I have to teach both fields in our regular BSc program in Stuttgart, I usually do it the other way around. I start with this and then I talk about thermodynamics. Okay, now our students also know classical mechanics on the level of Hamilton's equations of motion, of Liouville's theorem. And as I will show you, this will be my first main point, is that you can get the students within quite a short time to the point, to one of his most spectacular recent results, which is the Yavinsky relation, by starting here. And this is something I want to show you first because it's one possible point of entrance to this new field. And if they know thermodynamics, I can remind them with this slide on what they have learned half a year earlier. So a typical experiment, as you know, you have this piston, you move that piston in finite time to a second position. You do that while the system is in contact with the heat bath. This will cost some work, and then thermodynamics will tell you by the first and the second law that when you combine these things, since the students are not yet here, we don't have to go through the details, that the dissipated work, i.e. the difference between the work spent and the free energy difference associated with these two equilibrium states, that this dissipated work is always positive. Okay. So this is known for essentially 200 years. And then Jarzynski came and developed a new relation, which I should presumably have boxed here. Who in this room does not know the Jarzynski relation? Everybody does. Okay. So what is the point for this presentation? The point is that you can derive it using classical mechanics on essentially, you said 20 minutes this morning, right? Okay, so perhaps 30 minutes. How do you do this? You start with the Hamiltonian system, very much like the one Angelo had this morning. You have particles interacting, you have a piston interacting, and rather than applying a constant force, you have this piston attached to a spring, and then you can externally control the position of this base point of the spring. Okay, so now you imagine the whole thing is governed by Hamilton's dynamics. You start initially with some unknown, but still existing, some unknown but existing phase point in the full space. So these are 10 to 23 coordinates and momentum. And then by specifying lambda of t, you specify essentially the dynamics of this phase point. Now what is work is just the difference in energy. There is no heat bath here. So the work you put in depends on the initial phase point, and that's the Hamiltonian at the final phase point, which is a function of the initial one minus the original energy. Now, the key assumption is, for this derivation, that initially the system is in thermal equilibrium, referring to that position of the initial control point, lambda naught. And then, as I said, Jarzynski relation is this one. I will derive it later, but can be stated here. And of course, the surprising fact was that while the right-hand side is an equilibrium property, the left-hand side is something which depends on how you move from lambda naught to lambda 1. So that's a non-equilibrium quantity. And once you have this, these are averages with respect to this initial condition. Once you have this, it's trivial by Jensen to get the second law in this form. So this is one way of deriving the second law based on these assumptions. So how do you show students how to prove this? Well, it's actually a special case of what is now called or known as an integral fluctuation relation. And since that pops up several times in the field, it's good to explain this just once in a kind of general way. So suppose you have some probability distribution, P of x, and some function R of x. Then R obeys an integral fluctuation relation if e to the minus r average is 1. And if you assume you have this, then as a trivial exercise for students, you can show that you have to have events with negative r, except that the probability distribution is delta like at 0. The average is positive. The probability that it's significantly negative decays exponentially. And if you know for some reason that R has a Gaussian distribution, there is a relation between the mean and the variance. And this relation is just one of these integral fluctuation relations. And now I show you, remind you, that there is a whole class. You can easily generate a whole class of such distributions in the following way. You assume an initial distribution, like the Boltzmann distribution, gives Boltzmann, that vanishes nowhere in free space. And then you introduce a completely fictitious normalized distribution P1, and you evaluate this fictitious distribution at the final phase point given dynamics, which maps the C0 to the psi T1, i.e. the psi 1. And since this is a normalized distribution, 1 is this integral, and then you do a really trivial trick. You multiply by P0, you divide by P0, and you put the P1 over P0 as log in the exponent. It's totally trivial. Then you have an average here over the initial distribution, which are these brackets. And then if you identify this log in the exponent as this quantity R, you have an integral fluctuation relation for this R. And the only thing you need is that the Jacobian from C1 to psi naught is 0. And is 1. And that Jacobian is 1 because we have Hamilton's dynamics, because of Liouville's theorem. Okay. So what you realize with this is that any R, which is of this form, minus log of P1 divided by P naught, for any P1, fulfills such a relation. And then you can just choose what you want. And for Jarzynski, you take the fictitious Boltzmann-Gibbs distribution at the final point of the control parameter. This does not mean that the distribution is supposed to be thermal at the end of the experiment. It's a mathematical trick. And when you plug that in here, you get, just because the difference of the H is the W, the difference of the normalization is the delta F, you get Jarzynski. Okay, this you can do in 30 minutes if the students know Liouville's theorem for classical mechanics. Okay, it's nice. I always like to illustrate things which we do in theory with. Yes, please. Yes, please.
In principle, you can find an R even if the Jacobian is not 1, right?
Yeah, then you have an additional correction from the log of the Jacobians. Yes.
So that way can be made more general.
Yeah. It's a trivial generalization. Yes. Okay, so the first, I think it was really the first experimental illustration. I don't like verification, but illustration of the Jarzynski relation was with stretching RNA. As you know, RNA is half a DNA. It can map or fold onto itself in this kind of hairpin-like structure. And then you take these RNA molecules, you attach them to micron-sized latex beads, and then you move these beads by optical tweezers or micropipettes in a controlled way, thereby unfolding this molecule. Then you get force distance curves, and the different colors refer to different velocities with which you perform this experiment. So if you pull fast, you get these traces, and with these traces it's nice to illustrate the effect of fluctuations, right? These are 50 repetitions, in a sense always the same external conditions, but you get very different points where the molecule folds open and refolds. And then when you measure the work, because work is force times distance, when you measure the work for different velocities, you get different histograms. And the 2 key points are you have events here left to the 0 and dissipated work is actually negative, which some people have called violation of the second law, but I do not endorse this kind of formulation. And then you can, for instance, recover the delta F from these experiments as shown in this paper. So what is important about this derivation of the Jarzynski relation? In a sense, it provides a rigorous proof of this particular variant of the second law. I mean, it's a theorem. If you start initially in thermal equilibrium, it's a mathematical consequence. It does not claim, I emphasized it does neither claim nor require that the final distribution is Boltzmann-Gibbs-like. It is not. But that's never assumed. That was one of the mysteries in the original discussions. And by the way, the derivation I've shown you was not Jarzynski's original derivation. The system can be tiny, like a single molecule, but of course it must be coupled to a thermal bath. Somewhere we need the large N from this one. And I think that's key too, and also very revealing. You never have to talk about entropy. I didn't talk about entropy yet. You don't need entropy. You can turn it around. If you want to talk about entropy, and I'm just repeating what Angelo said, you need this kind of coarse graining. You need it either coarse graining or you need stochastic dynamics. If you stay strictly within this Hamiltonian realm, there's no need to talk about entropy. Okay. So this was one entrance, or one way towards these new results for students who know Hamilton's dynamics. If you have students who don't know that, and if you want to talk about entropy, you have to do some kind of coarse graining. Now, if you want, forget everything what I've told you so far, and you can also start with something like this. You can start with a closed system in thermal equilibrium. You have microstates with a certain energy. You put that system in contact with a heat bath, and then you do some coarse graining. So it's hard to see, but here are different conformations of a protein or molecule, and you know if it's closed or more or less closed, you put it as one mesostate I. If it's open, unfolded, you call it J. So you have mesostates capital I, J, K. Then, if the thing is in equilibrium, you know that the probability to find a certain mesostate is given by the sum over the microscopic probabilities. You can now define, just definitions, you can define a free energy for each mesostate, you can define an internal energy, and you can define what I like to call the intrinsic entropy, which is just beta E minus Fi, which turns out to be the Shannon entropy of the probability distribution, constrained the fact that the mesostate is capital I. Okay, so this for most students presumably will be a reminder. Okay, now we want to do dynamics, and then the second basic assumption is that you have chosen the mesostates in a way that equilibration within each mesostate is fast and transitions between the mesostates are slow. And then you can apply your timescale separation, and then you'll have a Markovian dynamics on the level of the mesostates. Okay, when you have Markovian dynamics, and for you this was the point of departure in your models, you have the fact that the probability to be at time t in state I changes with the rate kji, you go from j to I, and with the rate kij, you lose probability to the states j. Of course, you can always write, I mean, once you have a master assumption about the stochastic dynamics, you will always write something like this. But then the question is, where do you get the rates from? And this is where stochastic thermodynamics come. It's not like in this morning, where we make certain assumptions about the rates, alpha, beta. For these kind of systems, and my claim is, for essentially all molecular and cell biological systems, temperature is still a good notion. You know, in our bodies we all have 37 degrees. We're out of equilibrium, but we all have 37 degrees temperature. And this helps enormously, and that's one of the cornerstones of stochastic thermodynamics, because that leads to thermodynamic consistency. What you want is, when you start with this dynamics, what you want is that the Boltzmann-Gibbs distribution, if you're in equilibrium, stays invariant. And you want no net flow across any of the links, because otherwise you would have a driven system. Now these two requirements uniquely fix the ratio of the rates. They don't fix the individual rates, but they fix the ratio. That's conceptually important, and when you work that out, you find that the ratio of the rates is e to the minus this free energy potential, which I have defined or identified previously for each mesostate. So there is, you can't use anything else. In particular, you're not allowed to use rates which go only one way. Okay, if Kij is non-zero, Kji better be non-zero too. Otherwise you violate thermodynamic consistency. By the way, many models in cell biology do violate this. I find many papers. Of course, the backward weight may be small, but you should not assume that it's zero. Okay, now, once you have this set up, I've introduced it as an equilibrium problem, but it's easy to see that it now will also hold for any problem where you have initially a condition which is not of the Boltzmann-Gibbs type. You can start with any initial condition as long as you have this timescale separation. You can still use that, and then you will run into the equilibrium, of course, using Perron-Frobenius, as explained this morning in a slightly different context. Okay, now we have thermodynamic consistent rates. Now we even have thermodynamics on the level of individual trajectories. How does that work? And the basic idea, I think, is due to Sekimoto, who did it for the first law. So suppose you're now looking at a trajectory like this one. Suppose the molecule jumps from I to J. Then its internal energy changes. Where does this energy go? We still believe in energy conservation. Well, it's coupled to a heat bath, so it has to be the heat dissipated with my unit, with my sign conventions, dissipated when the system goes from I to J. And since the heat bath is the heat bath with a well-defined temperature, we can associate with this Q a delta S of this reservoir. Now, it turns out that this is not the full entropy production along this trajectory. There is more to it, and I thought for a long time how to convince students best of this, this relation, which will come. And I think the most honest way is to introduce it as a new postulate. And the postulate is that entropy production along a trajectory is a quantitative measure for the breaking of time reversals. Okay. So suppose I'm looking at the time reverse trajectory, I tilde. So I'm observing an original trajectory I of t up to capital time, capital calligraphic T, big calligraphic T. Then I reverse the time, then I get this time reversed trajectory, and now it's a postulate. I think all kinds of derivations are not really honest, so I think we should take it as a postulate. That's at least my present knowledge. We define the total entropy production along such a trajectory as the log ratio of the probability of observing what we have observed divided by the probability of observing under the same conditions the time reverse trajectory. Okay, so please, I want to make clear what are the conceptually important steps. This is conceptually important, and I think we should take it as a postulate. And then you plug in these probabilities, no new assumption, and then you find that this entropy difference is what we have identified here, but there is something extra. And something extra contains two contributions. It's the energy, the entropy, the difference in intrinsic entropy. So if that state has more intrinsic entropy, that will be positive. And then there is this minus log p term, which I call stochastic entropy some 12 years ago. And it's this basically information theoretic part. Okay, so this is the postulate, and then this is the identification. Now, in equilibrium, it's easy to show that this quantity is strictly zero along each trajectory. So in entropy, in equilibrium, time reversal symmetry is not broken. If I show you a movie backwards, you can't tell me whether I show it the right way or the wrong way. If I show you a movie of an egg splashing on the floor and I show it backwards, you can tell me. Okay? Okay, so this was, and I like it, this idea that you do thermodynamics along trajectories. I know that not everybody likes it, so, but you can also do it on the ensemble, then you average the quantity I had on the previous slide, and then for instance you get the average total entropy production at time t. It's just given by summing over all trajectories with their probabilities, and that's something which Schnackenberg already did some 40 years ago. And then it's also trivial to prove another of these integral factorization decisions. So once we're here, my claim is we're done with all systems which are relaxing from a non-equilibrium initial condition. And I'm not showing this in detail, but it's true. We're even done with time-dependently driven systems in the sense that the rates become time-dependent because I apply time-dependent forces or time-dependent chemical potentials. Of course, still having the basic timescale separation. So if we drive so fast that equilibration within each mesostate does not happen on an even faster scale, then of course the whole thing breaks down and this whole Markovian assumption is gone. By the way, I don't mind if you ask questions. Okay. interrupt. Okay, next big conceptual step. The non-equilibrium steady state. And I don't want to postulate it, I want to introduce it. Because it's an important concept, also for instance for molecular motors. So we have now to go from a closed, perhaps driven system to an open system. Open in the sense that we attach reservoirs, and the essential role of these reservoirs is to provide particles at certain chemical potentials for chemical reactions. Because as you know, for instance, molecular motors, they are fueled by hydrolysis of ATP. So in our cells, ATP is a high chemical potential, ADP and phosphate are at a low one. So how does one introduce that? Well, one clean way is to first think about a big, still big, closed system where these different molecules are in there. And then, for instance, when the molecule steps, the molecular motor steps, some chemical reaction takes place, a weight is lifted, and then we apply the previous rule to the supersystem. So there is a change in free energy, and this change in free energy, for instance, for such a step, will involve the change in free energy of the motor, but it will also involve the change of free energy of the surrounding molecules, and perhaps if we step against a force, there will be some energy associated with that as well. And then we have still apply the old rule, what is sometimes called the local detailed balance condition. We then have the master equation, but if these chemical potentials and forces are time independent, it's sufficient then to look at transitions between the mesostates of the motor, and if these quantities are time independent, the whole thing will run into what is called a non-equilibrium steady state. Key point again, the rates are not postulated, but the ratio of the rates is fixed by thermodynamic consistency. If you do that differently, you can still work it out, but it won't mean something, because you're not guaranteeing that you run, for instance, into the correct equilibrium if you let the system run for long enough time. It has to reach thermal equilibrium even under these conditions of chemical reactions. Okay. I don't think I have to go through that in detail, but you can do now the same thing we did before for trajectories and for the ensemble. Let me jump just to the next slide, because now we have introduced in that course the idea of a non-equilibrium steady state. Now I like to show the students the simplest one. And the simplest one is an asymmetric random walk. You all know this master equation for the random walk. Most of you will know that you can find the solution in Frank Kamprand's book. It's one of the exercises, and typically let students solve that. And then when you look at this expression, you find that p of minus n, so the probability to do n steps into the left in the wrong direction divided by p of n is just exponential in n. It just follows from this expression in this line. Now, of course you know the asymmetric random walk, but you have to make sure that the rates are thermodynamically consistent. So for instance, if this is a molecular motor, it's driven by this ATP hydrolysis, and I just told you that the total entropy production is associated with breaking time reversal symmetry, and for the asymmetric random walk, the quantitative expression is just n times the log ratio between forward and backward step. Yeah?
I think here it's essential to say what the boundary conditions are, right? Are you thinking about this or are you thinking about it as a...
No, here I'm, oh yes, good point, Jonathan, thank you. Here I'm talking about a situation where initially the particle is at n equal to 0. So I mean, I'm counting steps.
Yes.
And of course, it's open to the left and right.
Okay.
And then this is true or this is true. There are no further conditions.
Because if it's on a ring, then of course the stationary distribution will just be uniform, right?
No, it's not on a ring. It's open, I mean, it's infinite boundary.
Okay.
Infinite, it's an infinite track for this to be true. it can be in a ring for this to be true.
But then it doesn't have a stationary state if it's infinite.
Ah, sorry. Oh, I see what you mean. Yes, of course. Well, because the system has only one internal state, it's in a stationary state. But if I look at n, it's not a non-equilibrium.
I mean, n. So okay, so your variable is actually not n, but the I mean.
Well, the ij variable from here has only one index. Yeah, so the ij is an internal variable which has only one index, and the n counting is basically, you know, how many ATPs have I used or how many steps have I made. So this is associated with the splitting here, basically the splitting between the capital IJs and the little IJs. That was a little bit fast here. And yes, so in order for this is true if you start at time 0 at n equal to 0, or it's even true on a ring if you just count, you know, how many steps did you make in forward or backward direction. So even on a ring this is true, but then n is the number of steps and not the current position, because that would be modulo 2 pi l. Okay, the important point is that once you fix the rates, the entropy production is also fixed, or the other way around. If you fix the delta mu of the chemical reaction which drives the process, the ratio of the rates is fixed, and that's the total entropy production. And of course, if delta S tot is proportional to n, you can also use that expression for P of minus delta S tot. And you have the simplest, you have led the students to the simplest example of what is called the genuine fluctuation theorem for total entropy production. Okay. At this point, I then like to talk about steady states, because students have now seen where this concept comes from, and it's nice to contrast steady states from equilibrium, or perhaps from a linear response regime, if the students know about that already. So key point, of course, is that the distribution is stationary, but it's not of the Boltzmann-Gibbs type. So this is for a continuous variable like a particle driven across this periodic potential. This is for discrete states. And the key point is theta balance is broken, so there are currents through links, which of course lead to a mean dissipation. And again, I'm repeating this, we still have to assume that within each mesostate the relaxation takes place faster than these kind of transitions. With this slide and the previous one, I like to introduce a second big paradigm. So far we have talked about discrete mesostates with rates between the states. The second paradigm of the field are systems which have a continuous degree of freedom, like a particle, basically kind of generalization of Brownian motion. You have a particle which is driven by some force across a ring-like structure, and perhaps Sergio will show us tomorrow the experiment. And that's actually where Sekimoto derived this idea of a first law along trajectory. So typically we're in a regime where we can ignore inertia, system is overdamped. Important point is, even though the system is driven by a non-conservative force, because of this timescale separation, this is the equivalence. You can assume here that the stochastic forces, the noise is still delta propagated. Okay, and then you identify work, energy, and heat, essentially from this equation in the way that this box holds. And again, if you include this stochastic entropy, then you get this integral relation, or you can get this kind of second law variance. Again, it's important to emphasize this is not a derivation of the second law, because we have put in irreversibility when we broke down modular equation in the first place. Okay. And so this point one can state that this fluctuation theorem holds much more general. It holds for any stochastic dynamics, and I like this experiment we were involved with 10 years ago. because it shows one interesting aspect. So this is actually the measured entropy production according to the definitions I've shown you for this kind of system, where this is the histogram of the total entropy production after 2 seconds. So you see it's a kind of bimodal distribution. After 20 seconds, the black curve is trimodal. And this peak structure arises from the fact that after 2 seconds, the system typically has stayed within the original well or has made one jump. And roughly speaking, entropy production is force times distance. So if you go once over the barrier, you have a certain unit of entropy production. And if you go twice, you're here, or 3 times you're here. These are very non-Gaussian distributions. Still, if you plot them logarithmically in this ratio fashion, you get a straight line. This is the slope, and you see the experimental line. Okay, so how to prove that? Again, it's rather simple. We started from this definition that the log ratio of a time reverse pass with respect to the original one is minus the total entropy production, and then you just do trivial calculation. I guess all of you have seen that. It's 4 lines, and then you can prove this famous fluctuation theorem, at least in the stochastic variant. The original variant, or especially the variant like Alawotti and Cohen, was based on this chaotic anosov dynamics. But within the stochastic dynamics, it's again kind of triviality. And it holds for any non-equilibrium steady state. Okay. At this point, I usually like showing students that in real life things may be more complicated than in an ideal situation, because there is again this kind of experiment, and in that paper the original researchers used that concept of the fluctuation theorem for this molecule. And if you assume that you have a kind of continuous Brownian motion along the angle driven by some torque, you would have this simple Hodgman equation, and then of course it's again a triviality. But when you look at the slope, which should be 1, or in this representation you would get the torque in units of kVt. If you look at the experiment, these are the distributions of this angle after certain times. You get something which looks more or less linear, but if you look at the slope, it has a time dependence, and it should not have a time dependence. Why does it happen? Well, the reason is that this construction is more complicated than this equation. There are hidden degrees of freedom, because you don't even see when this motor moves, you only see this attached bead. There is some elastic linker in between. So what we have here is a simple example of the effect of cross-graining. We see only 1 degree of freedom. We have a hidden slow one. That's too much cross-graining. And then one can, if one wants to follow this path, or one can students let either come up with a better model or show them a better model, and perhaps I should show you that very briefly. So if you do a model where you have at least 2 degrees of freedom, you keep that big bead, you keep the motor snaps in a chemical reaction, and then it displaces this elastic linker, and then it either steps back or the bead follows. Then you have 2 combined systems. Let me jump over this briefly. This is something students can do in simulations. You let them generate this probability distribution. You let them look at the slope in the fluctuation theorem representation, and they find exactly what you find in the experiments. And again, you can even let them, let me jump over that, you can even let them calculate or investigate the efficiency of that motor within the simple model, and you get rather nice agreement. So I didn't go through the details here, but I think it's a nice example for a student project or for a seminar talk for students, because it's a simple system, there are real data, and simple theory leads to a rather reasonable agreement. And I think it's important for them to see real world data and try to understand them.
No, but I don't understand your point before, because They use actually okay, no, I understood the fact of hidden variables, okay, but you said that it's strange that they have the slope of the fluctuation theorem is it depends on time.
Yeah.
They use not your entropy, they use just the work. So they have to find anyway an asymptotic. It's an asymptotic statement, so in any case it will depend on time.
Well, it's correct what you say, but the shocking effect is that if you take the asymptotic value for the top, you get it wrong.
Okay, but this is another story.
You get it wrong, you should take the time equal to 0. Yes, but I mean, you know, if when they try to, or when they were using just this kind of relation, there is no stochastic entropy if you believe this, because the stationary state is just flat, and then in principle they did the right thing.
Yeah.
So this is too simplistic, and you have to keep both degrees of freedom. You have to do.
No, but that understand. But in any case, even if you do this correctly with another variable, you will have using this definition of work, you will have an asymptotic statement. It's not you will depend time anyway.
Yeah, I agree. Okay, so in the last 5 minutes, let me show something which is a little bit more new. And I think, again, of course, it's a little bit a personal thing, but I think it's important to show students that you can use these tools even to derive things which you did not know before. The fluctuation theorem and the Yarczynski relation, in a sense, are identities. So there is no point in testing them. What you test in these experiments, and I hope that you will agree, is whether your experimental system conforms with the assumptions which went into deriving the theorems. But in this very last part, I want to show you something which we discovered recently, which again is so simple that you can tell students, introduce students to it. And I think in the long run this will be hopefully a rather important tool for what I like to call the thermodynamic inference. So this is what I've told you before. As you know, if you measure the number of steps after a certain time, you get an average value, but this comes with a certain variance. And now let me define this as a process which has a product. The product are steps, and I want this process to be precise. You could also think about the steps on this kind of old-fashioned analog watch. So the uncertainty of the outcome of the process, I define the uncertainty as the variance divided by the mean squared. I emphasize the fact that all these processes have to be thermodynamically consistent, so whenever you break the symmetry, someone has to pay for it, so there is a constant rate of entropy production. A is the affinity, which is the log ratio. These are just the relations I've shown you so far. But if you combine those, you find, and that's the interesting aspect, you find that the cost of that process times its uncertainty is given by this expression, and this is bounded from below by 2 kBt. So if you want a high precision, i.e. epsilon small, if you want a precise watch in a finite temperature environment, you have to pay more. You can't beat that bound. This is derived here for the asymmetric random walk, and any student could do that. Turns out that this is true for any Markovian network of states. If you have a complicated watch, which does at the end steps, but has some complicated, sophisticated internal wiring, this relation is still true. So for instance, if you want a watch which is precise with 1%, so let's say after 1 hour you don't want to have an error which is more than a minute. You have to pay 20,000 kBt for running this clock over this hour. And you can't beat that bound. It's a universal bound. Okay. One nice example how to use this is to derive a bound on the efficiency of molecular motors without any further assumption. So this is again one of these motor experiments. We let the molecule run against a force. We impose a constant force by some feedback having the speed at a fixed distance from the position of the laser. Then you get data. You measure the velocity. You measure the spread in velocity, which is the diffusion constant. and then or some ratio is called randomness parameter as a function of the ATP concentration, i.e. the driving force, for different forces for different loads, or you do it as a function of the load for constant ATP concentration. These are all data from Block's group, 20-year-old data. Now you apply this, what we call the uncertainty relation, to get about on the efficiency. What is the efficiency? The efficiency is the power output divided by the power input. The output is force times velocity. The input is unknown. You don't know how many molecules this motor uses. But you know that the input power is this what you get out plus this what is dissipated. And we have a bound, we have a universal bound on the entropy production. Okay, so the cost is the entropy production. We have a universal bound on the entropy production. So we have a universal bound on the efficiency, which involves the measured velocity, the measured diffusion coefficient, and no other parameter. We take the data, the 20-year-old data, and we plot here the efficiency. This is the bound. This is 80%, 70, 60. So, for instance, you can say on the basis of this result that the molecular motor which led to these data points is at most, let's say, 65% thermodynamically efficient. Without any further assumption about how the motor works. You don't even need to know the concentration of the ATP or the ADP, which is often hard to measure. And I think that's a really interesting, important result, which should students convince of the fact that with these tools we can learn something new about relevant systems like molecular motors. And I think I want to close with this. I did not show you how to derive this thermodynamic uncertainty relation. This would need techniques from large deviation. You put large deviations in my title. I have 7 more slides on it, but I will skip those and rather tell you, yes, you have to use large deviations. It's of course nice if you're theory students to introduce them to the field. If you want a proof of this relation, it's I think a non-trivial relation, but I think it's also more important in this context to show that you can really use it, and hopefully at some point biologists will use it for their molecular models. So let me briefly summarize. In my opinion, what I've shown you is accessible, and we do that in Stuttgart in a bachelor program. This theory, in my opinion, is systematic. It's as clean as classical mechanics or quantum mechanics. It's not some dirty theory, it's really clean. There are different methods, stochastic dynamics, this. You can do simple simulations, and I think that's also important. Quantitative comparisons, and we'll hear more on this tomorrow from Sergio, with single molecule or single colloid experiments is possible. That's an additional asset for such a course or for such a topic to get students interested. Thank you very much.
Questions? Okay. A question about the last point. I mean, it's accessible in the BSc program, but how do you actually practically do it? Because they need to know, as you said in the beginning, they need to know basic statistical mechanics. They also need to know some stochastic processes, right? And so, where is the space to introduce all of that?
Well, I mean, that's a different question. Whether there is space. I mean, the point is whether it's intellectually possible. And for instance, I do Jarzynski when I teach. We have in the 4th semester, in the 5th semester of the BSc, we have a course on statistical physics. And there I do big parts of this. I do the Jarzynski with the stochastic dynamics, I do Fokker-Planck, I do the diffusion equation, I do the path integral, which I didn't even show you here. So you can do that. Of course, then I don't do much on phase transitions, for instance. So of course you have to decide. But it's not that you need tools which you cannot introduce. I mean, you don't need Feynman diagrams or group theory to do that. And you know, if I was free, I would reshape our PSC program. I would make room for it, more room.
Any other questions? I can say one more thing. Just about this bias random walk, to come back to that. I mean, you know, the way I think this is most useful in a pedagogical way is to make clear the distinction between equilibrium and non-equilibrium states, and also to sort of explain the notion of thermodynamic consistency. So the way I like to use this is to say, okay, this is a particle in the field. You close the system, it will run to an equilibrium state. So then you basically derive what the ratio of the two rates should be, and you have a globally defined energy, so you can use the Boltzmann distribution and everything, and then you put it onto a ring, then it's out of equilibrium just because of the boundary conditions. You get a completely different stationary state, but you now have a current which you can, because of the thermodynamic consistency, you can immediately translate into entropy production, for example. Right? So I think in that sense, this is, you know, I would put this at the very beginning, because I think this is really, yeah, I think this is sort of what, you know, as soon as you start saying what a non-equilibrium stationary state is, I think this is...
You would do that before you do relaxation, for instance, or time-dependent rates. Yeah, it's perfectly good. But you can do it like this, sure.
You were mentioning at some point during the talk that essentially Jasinski and the fluctuation theory are essentially identities.
Yes.
And then, as you were saying, they can be used as check if an experimental setup. These conditions of the conditions for which these things fall are fulfilled. But this is not an easy concept for students, because they always look at the, I mean, how to say, what is this useful for? I mean, but then you have to introduce all the examples to explain why all that is useful.
Well, originally, of course, Jasinski was sold as a tool to get free energy differences, right? But then the practitioners have realized that the error bars of this nonlinear average are so bad that you probably better do just a linear response regime, right?
Yes, but okay, but this is just a matter of presentation. Is this say from the very beginning, or is it just something that has...
Well, I mean, you know, I'm serious that I'm not not mainly doing numerical experiments or numerical work. So I like to present theorems first as a result, and then only talking about, you know, how much statistics do you need and so on. So of course, and you know, my personal excitement, why did I enter this field? I mean, when Jasinski wrote this, I did something completely different, membranes. And I got into the field because in 2001 I came across this paper, and I didn't believe it. Like, you know, no sensible person should have believed it when you see the Jasinski relation for the first time. So I started doing calculations. I wanted to understand it. At that point, I moved to Stuttgart. They asked me for a kind of inaugural presentation, and I said, "Okay, I'm talking about this one. I want to understand it," and that's how I entered the field. So it changed my scientific life completely. So I certainly present it as something important, not just not just as a tool. And then, because then people will tell me, like the Kramer and others, well, Delago, of course it's hard to use it in order to get big free energy differences. But for instance, if you do Crookes, there are these nice experiments by Felix Riton with the chemical reactions where you have for 70 kBT delta F and you get it nicely. So. But that's the difference, you know, I think theory, I mean, one thing is what are the theoretical results, what are they based upon, and the other is, you know, how do you use it in practice? And perhaps in practice these relations are not so important, but on a qualitative level, of course, what you get is, if you get something like this, you know that you haven't checked for all hidden degrees of freedom, and of course there's now a whole subfield trying to work out the effect of these hidden degrees of freedom. So in that sense it's useful, but it's hard to learn something. I mean, I think all these fluctuation theorems about entropy production, we did not learn something about entropy production which we didn't know before for a specific system. I don't know if researchers will see it differently. But this new thing, this entropy relation, is something useful. I'm deeply convinced of that, and this molecular motor reanalysis of the old data, I think, proves that. And there's more to come there. We have now, but this was not supposed to be a scientific talk, but we can now, for instance, we have statements about the minimal requirements for having coherent oscillations in biochemical systems. How much delta mu do you need in order to sustain oscillations over 100 cycles, 1,000 cycles, and so on? So, I mean, this is very active field right now in research.
If there is another question, okay, let's thank the speaker again. We have the first student session, so we can get the program.